Try that again. Let's see. There we go. We are a recruiting platform, so our mission statement is to eliminate the gaps in the hiring experience. We primarily do this by 3 main points. 1, we're very customer focused within our culture. 2, we've gotten quite a few different awards for technical innovation. And 3, we really are the experts within our market. A lot of our C-level executives and a lot of our product people are individuals that have done recruiting for many, many years. So this allows us to build a wonderful product. That was my little plug for Yellow. On to the fun stuff. So as I go through this agenda, I want to see a raise of hands of people who feel that they're comfortable with these concepts. This is going to help me kind of understand what to focus on, what to skim over. So just raise your hands if you're pretty familiar with join types. Okay. Set operators. Okay. Filtered aggregates. Okay. Grouping sets. Oh, that's actually kind of surprising. All right. Subqueries. Okay. Window functions. CTE'S. Okay. Lateral. A lot less. Okay. So as I go through this, I want you to stop me and ask questions. It's going to be really difficult for you if you wait till the end because you're going to forget whatever it was that you didn't understand. So I would much rather you stop me and ask questions as we go through this than have you walk out not understanding the things that we actually talked about. Nod agreement. Yes, you will ask questions. Perfect. Okay, so when we first start learning SQL, a lot of the times we say, oh, I know what a basic SQL syntax statement is. We start with select something from some kind of table. Maybe we have a where condition of some sort, and then we order our output. Then, as we get a little bit more familiar, we start saying, oh, maybe we can join multiple tables together and do the same thing. Then we go, oh, now I know how to do aggregates, and I can do a group by, and maybe even filter my output by those aggregates using having clause. And then you look at the documentation, and it looks something like this, and then it continues on to this, and then it continues on to this. So it's actually a lot more complex than it seems at first. So we're going to go today through a lot of these concepts, not all of them obviously, but many of them. So since most of you are quite familiar with join types, I'm going to skim through most of these and focus on just one. Who's used a cross join? Who knows what a cross join is? Okay, so the disparity is actually quite good. You don't want to use it very often. But for those in the room who did not raise their hand, a cross join allows you to get a Cartesian product of 2 tables. So what does that actually mean? Let's say we start with 2 tables. We have stores and we have products. And let's say you want to understand what is your potential inventory in every single store that you have. So you could write this using, Clicker really isn't that great, guys. Okay, so you can select from your stores and cross-join to products table. Notice that when you do this, you don't actually specify any kind of criteria for joining your 2 tables. And the output is going to look something like this. You're going to have every single store listed with every single product. So it makes sense why you really probably don't need to use this very often, but it's good to know that it exists because it does have some special use cases. Any questions? Not if you understood. Okay. All right. I'm going to need you guys to embed these 2 tables into memory because I know that's really easy to do, because we're going to reference them repeatedly throughout this talk. So essentially, we have 2 tables. We have a customers table, and we have a suppliers table. For each of them, we have a name of customer or supplier, respectively. We have the city, the postal code, the country, and for our suppliers, we have their annual revenue. So we're going to work with this data set throughout. So, set operators, union versus union all. Let's say I want to get a list of all cities that span both my customers and my suppliers. I would do this using a union all. One of the things you'll notice is that union all allows you to have duplicates. So in this case, because I had both a supplier and a customer within Chicago, Chicago appears twice within our list. Now, if I want to get the same kind of list, removing all duplicates, I would simply do a union. So you can see now Chicago's there only once, and we have a distinct list. Any questions on this? Okay. So we have a couple other set operators. We have except, which does exactly what it sounds like it does. It gives you everything from your first data set except what exists in your second data set. So in this case, again, we're using city as an example. I'm pulling all of the cities from our customers table except for the ones that also exist within the suppliers. So we're left with New York, Stockholm, and Minsk. I can do the reverse of this and say, oh, I want to get an intersect, so something that exists in both of my result sets. And in this case, we get Chicago, because Chicago rocks. Okay, filtered aggregates. This was introduced in 9.4, so it's somewhat recent. It's actually very convenient. So in the past, if you wanted to, let's say, get a total revenue, but then I also wanted to show from all of my suppliers revenue just for the US. To do this before, I had to do something like this. So I could write a sum where I have a case statement embedded into my aggregation that filters out for the US and only counts the revenue then. So this is convenient from a usage perspective, but it's difficult to read, especially if you have a lot of these. Now, you can do something like this. So you can specify, let's see, there we go. You can specify a filter clause and then just write your where clause in parentheses, and this will do the exact same thing. So it's not mind-boggling, but it's very convenient from writing syntax perspective. Any questions on this? Okay. I have a feeling we're going to spend some time on this one because it's fairly new. So grouping sets were introduced in 9.5. And essentially what this allows you to do is it's an extension of the group by. And what it allows you to do is perform a group by for different subsets within your data. And essentially what that allows you to do is create totals and subtotals and have them displayed in a single result set. So in the past, if you wanted to do this, you would have to do it either through some kind of subqueries, or maybe you could do it through union statements by having multiple different selects and then unioning them into a single result set. Now you can do this through grouping sets really conveniently. There are also a couple essentially shortcuts within grouping sets for things that are commonly performed. One of those is ROLLUP, which allows you to do hierarchical, going up a particular direction, subtotals of your data set, and cube, which lets you do the same thing but in any direction of your result set. So we're going to look at a couple examples. So in addition to our customers and suppliers table, now you can remember the orders table. So in this example, we have a reference between customer ID and supplier ID. We have the date of the order and the dollar amount of their order. So in the past, if I was using a regular group by, let's say I wanted to pull my country supplier, the order month, the customer, and the total sum of orders, as well as the average and the number of orders. So I would do it like this. I would have my basic group by that has my country, supplier, month, and customer name. My result set would look something like this. That's pretty standard. I'm sure most of you have seen this before. Now, let's say rather than doing this, what I actually wanted was to get a subtotal across the countries, across the suppliers, across the order month, across my customers, and then across all of those attributes. So I would rewrite this in this way. Now, I've modified my group by statement to reference a grouping set, and within that grouping set, I've specified each individual component for which I want to get a subtotal. And this empty parentheses in the back just means group across all of them. So normally when I do this, the output looks like this. So you can see though in this display, we have all of our aggregations to the supplier level, to the customer level, and to the order month level. and then a complete total across all of them. Now, you'll notice this has a lot of nulls in it. That becomes very unreadable from a human perspective. One, if you're providing this to your end users, they may not know what that means. Two, if you have a data set that actually contains nulls, this is obviously going to be a problem. You have no idea if this is grouped or if this is actually null values in your result set. So obviously, we want to fix this. So we add this additional case statement within our attribute list. So rather than specifying that we just want the supplier name, we put a case statement and say, if the grouping of the supplier name is 0, which means that this particular record was not grouped, then display the actual value. If it was grouped, let's replace it with some other syntax. So in my case, I chose all suppliers, all months, all customers. You could obviously make this look however you want. So then our result set looks like this. And this becomes much more readable to the human eye. Are there any questions on this?
Can you go back to the previous? Yeah. So the grouping set statement doesn't change?
Correct. Yes. So the group by over here has stayed the same. The only thing I changed is the way that the attributes are actually displayed. Does that make sense?
So that grouping statement up there is like, that kind of goes with the grouping set?
Yes. So it's essentially a keyword, like a function, that's provided within the grouping sets functionality that allows you to check for any given attribute or any given column name whether that particular row has been aggregated up. So if it's 0, that means it's the raw row level detail. And if it's something other than 0, like 1, that means it has been grouped. Any other questions on this part? Okay. So, all right. So as I mentioned earlier, ROLLUP is essentially a shortcut for a type of grouping set. What it allows you to do is create a specific hierarchy and then aggregate up that hierarchy. So in my case, let's say I've decided to create a hierarchy for country, supplier name, customer name. So when I specify this ROLLUP keyword, this on the back end converts it into a grouping set statement that actually looks somewhat complicated and that I did not include. But the output looks like this. We start out with the most granular level, the way you would in a normal group by statement. So we're grouping by supplier, country, supplier name, the customer name, and we have our aggregations. Then we go up one level. We aggregate across our customers to the supplier and country level. Then we go up one more layer across suppliers to the country level, and then one more layer across all of these attributes. So it's a pretty nifty way to do grouping sets without having to write out every single set. Does that make sense? Questions?
So
Yeah.
you didn't know to call it all suppliers or all customers. Was that in your previous statement?
Yeah, so let me...
Where does it come up with that?
Yeah, so
Oh.
so from now on, I've used this case statement because otherwise I figured it's going to be really hard for you guys to follow what's an actual aggregation and what isn't. So basically in all of these, I've provided these case statements up here. Any other questions?
The order of the to roll-up, does it matter?
The order of the roll-up does matter. So you have to specify your highest grain to lowest grain. Whoops, sorry about that. I guess I won't put my arm in front of myself. Yeah, so you're basically specifying what the order of your hierarchy is because the roll-up goes only in one direction. Any other questions?
What happens if you don't do the correct ordering?
So if you don't do the correct ordering, it'll, so over here, you can see that it grouped in a particular way. So what it'll do is it'll just group in a different order. It'll group in whatever way you defined. So for example, if I had said supplier country, then customer name, and then supplier name in my hierarchy definition, then the way this would look is the most granular level would look the same. But then what I would have is at the next level, rather than aggregating, rather than aggregating across all customers, I would see the individual customers, but all suppliers. And then it would keep going. Any other questions on this? Okay. Let me fast forward. Okay. So cube is very similar to rollup, with the exception that rather than going up a particular hierarchy, it actually goes in every single direction of the hierarchy that you define. So rather than being hierarchical, it's multi-directional. So in this case, I've also shortened my result set and filtered to only a couple customer IDs, because otherwise my result set is going to be huge and it doesn't fit on the slide. But essentially, so I'm doing a cube of supplier name and customer name. So I want to be able to aggregate. We start out, this looks exactly like a roll-up statement, right? So we start out with the most granular of supplier and customer, and then we aggregate up to the supplier. So this looks the same as our initial roll-up would have looked. But then we also have it going in the other direction. So we're aggregating across our suppliers and to the customer level. And obviously, the most aggregated total across all of them. Does that make sense? And does the distinction between roll-up and cube make sense to you guys? Yeah?
Is cube just roll up plus roll up backwards, basically?
Basically, yeah. And in my case, I limited it to 2 fields, whereas if you had 3 or 4 fields, it would be every level of every direction. So you have to consider that when you only have a very limited subset, in theory, there's only 2 directions. But as you accumulate more columns, you actually end up having any number of combinations. And cube will get you every single combination. Any other questions?
Sorry, can you go back one page?
Sure.
Oh.
No question? Okay. Yeah.
Would you create more performance impact, like when you have more number of columns and number of rows which are selected becomes more?
Sorry, could you speak a little bit louder?
Would cubing more number of columns cause any kind of a performance impact? Like, is that something which is discouraged, or like cubing is encouraged?
Okay, so the question is, the more you add to the cube, obviously it's doing more. Is there a performance lag, right, or performance cost?
Yeah, and is that encouraged, or like, just like a Cartesian product is like, it's okay, but like it's not really encouraged to use.
I think it depends on your use case, right? So in the end, you can't really specify best practice holistically when it really depends on your use case, and it really also depends on your data sets, right? So there's some SQL functionality that will be really efficient in one person's environment and really inefficient in another person's environment. So it's hard to say. In general, will there be more of a performance hit? Yes, because it's performing more, right? It's doing more calculations. But at the same time, if you consider the benefit of doing it in a cube versus, let's say, doing individual select statements and then trying to union them all, this is probably going to still be more efficient, right? So if you need the functionality, then this is going to be a better way of accomplishing it than the other methodology that's available. But is it necessarily going to be the most efficient thing in the world? Probably not, especially if you're putting in, let's say, 10 or 15 columns. Yeah, that's going to blow up your result set. Yeah?
Can you give an example, a more real-world example of where cube would be the right solution? Where it would be the necessary way to present data?
Sure. Let me think of a good one. I suppose, I mean, I guess to me, something like this, even though this is obviously a really cursory data set, would be a real life example, right? If you're an organization that has multiple locations and you have different clients around the world, and let's say you're trying to analyze where do you see insight, what is most, like what are your most valuable customers versus what are your most profitable locations versus what are your most profitable actual products, right? And so you could do each of those analyses independent of one another, or you could do them in a single statement, see all of the insight, and then say, oh, well, I think these two things are the most relevant. Does that make sense? Any other questions on this? Okay. So, subqueries. This will probably be a little bit easier because I think many more of you have encountered this. So we have two types of subqueries. We have uncorrelated subqueries and correlated subqueries. We're going to start with uncorrelated. So essentially, an uncorrelated subquery is it's calculated once, and then it's utilized within your outer or upper query. So it looks something like this. Let's say I want my list of suppliers and city of my supplier for all of the suppliers where the country of the supplier matches a country where I have customers, right? So in this case, I did a subselect. I selected my country from my customers table, and I put that into my filter where clause. And my result will look something like this. Now, in the reverse, a correlated subquery actually references your outer query within its definition. And it gets executed once for every single row within your outer query output. And a lot of times we can also rewrite these as joins. So let's look at the example. Let's say now, rather than just seeing my suppliers that have customers within their countries, I want to also get a count of customers that exist within the same country as my supplier. So in this case, we put this as an actual element within our select clause. And we have the subselect where we're doing a distinct count from my customers table where the customer country matches our supplier country. And our output looks something like this. Yes?
When you say there are recursive for every row, do you mean that literally, or do you anything fancy for you? Like I noticed it because the query join it.
Yeah, I mean, it obviously optimizes it on the back end. It doesn't do like crazy things. It's not equivalent to, let's say, writing 100 different statements per every single row. It optimizes it. But what it does is it's the distinction of calculating your subquery once and then having it be referenced as a whole versus calculating for the individual rows within your outer query. So one example that you can see here is in this case, I'm running this statement across my entire customers table, even if the country of this customer isn't a country of my supplier, right? Whereas here, I'm doing this limit. So I'm only performing, come on. All right, laser pointer might be dying. I'm only performing this action for the specific rows within the customer table that actually have the same country as my supplier table. So it's acting as a filter as I'm going through it. And it applies that filter per row. Does that make more sense? Any other questions on this? Okay, so this is what our result set would look like. Okay.
Can we go back?
Yeah.
How would you optimize the previous query?
How do you optimize what?
This query. So you said that often can be rewritten as a join.
Mm-hmm.
Then you're implying that since the subquery will be performed for every row
Yep.
at some level, is there a way to optimize it by rewriting the statement?
So what ends up being more optimal actually depends a lot on your environment. So typically when I'm writing a lot of complex SQL, I end up having to test and check my actual execution plans to see what's better in my given environment, because it really depends on your table size, it depends on your indices, it depends on a lot of factors. But one way that this could be rewritten is that I could say from suppliers, join my in this case, I could do an inner join, right? So I could join customers on C country is equal to S country, and then just do a distinct count of customers that way. But if you end up having to perform some really convoluted behavior, so a lot of times this will be used if you need, let's say you don't want to group your entire data set, but you need to get some particular count or some particular aggregation, right? Because ultimately you have to be careful that your subquery in this case has to produce only one record per row, right? It can't produce multiple rows per your outer row. So it has very particular use cases. Does that make sense? Any other questions on this?
Yeah, I have a question about the syntax.
Yeah.
So the alias customs score CT.
Yep.
Is it necessary, like, to put it in this case?
So in this case, this alias isn't actually for the inner subquery, it's for my labeling in the result set.
Yeah.
Right, so I'm in this particular case, the alias for my actual table is C, and I'm aliasing my entire output because otherwise, when I display my result set, it's going to be a nonsensical header.
So the execution plan, how much do you think is going to change if you rewrite it and make it a join, like inner join?
I've actually seen it change a lot. I've even seen it for like uncorrelated subqueries. The difference between specifying a list or a subselect for, let's say, 4 records, I've seen it in Postgres look completely different, change the order that it does everything in. So it really depends on environment. I think it's really difficult to predict. Any other questions? Okay. All right. Who attended the talk, I think it was yesterday, that went over window functions and CTE'S? Okay. All right, good. So hopefully this will be somewhat a refresher for you. Okay. So what is a window function? A window function performs some kind of calculation across a set of rows that are in some way related to the current row. What does this actually mean? What this means is it allows you to perform an aggregation the way you would any other aggregation, but it allows you to retain row level detail. So it basically allows you to look at other rows in your set, make some kind of conclusion about them, and include them in this specific row. So the times when you would really want to use window functions is if you need to perform calculations or aggregations while not grouping up in any way and retaining row level detail. So we're going to go over a couple examples of this. So to start off with, this is the syntax for window functions. So it looks kind of complex. We'll break it down in a little more detail. But high level, you have some kind of aggregation, an over clause, then your window definition, and an optional frame clause. So what does this mean? The frame clause essentially specifies which rows get included within your window. So there are a couple different options for this. It can be displayed as range or rows, and then either just a frame start or between a frame start and a frame end. We're going to review in a little more detail the distinction between range and rows, but high level, it designates how duplicate values within your rows are handled. For the frame start and frame end, we have a couple different options. We have unbounded proceeding, which means you start at the very beginning of your partition. We have value proceeding, which means you start a certain number of rows as defined by your value prior to the current row. Current row, obviously current row. Ending, same thing. Unbounded following means you go beyond your current row to the end of your partition. Value following, a certain number of rows beyond the current row. And current row is the current row. If you don't specify a frame clause, the default becomes range unbounded proceeding, which is equivalent to range unbounded proceeding with the end of a current row. So we're going to look at a few examples. All right. We're going to start with a really basic example. So let's say I want to display my supplier, my country, the revenue for that supplier, but also the average revenue across all suppliers within that country. So in this case, you can see that I've specified, I don't know where this thing goes. I've specified a partition by country, and when it shows my results, for the records where there are no other countries within the set, we obviously have the average matching our revenue. But once we get to the US, where we now have 2 suppliers, we see that the average is the average of the 2 rows that had USA listed as the supplier country. Does that make sense? Okay. Now, a little bit more detail about the range versus the rows. So like I said, range allows all duplicates to be handled within a set or a group, and it handles them simultaneously. Whereas a row allows you to go row by row and truly calculate, let's say, a moving average on a per row basis. So in this example, one thing to note is I removed my partition by. So just take note of that. But I did include an order by. And in this case, I'm ordering by the country. And I'm saying that we have range unbounded proceeding, which is also the default. So in this case, as we go through our result set, we can see that we start out with Canada, we have revenue is equal to this average. As we go down one, now the average becomes the average of the revenue for Canada and Spain. As we get to the US, because both of these rows have USA listed as the country, it handles them simultaneously. So the 412.5 is actually the average of all 4 rows in this data set. Now, if I were to change my syntax to say rows unbounded proceeding, now we can see that each of these rows is handled independently. Does that make sense? Does it make sense why you might need to make this distinction? Raise your hand if you're sleeping. Okay, just making sure. All right. So the other thing to keep in mind is a lot of times when we're writing window functions, we may have multiple window functions within the same select statement. Sometimes they're going to have different window definitions. Sometimes they're going to have the same window definition. If we have multiple references to the same window definition, it's easier to have a single reference where the definition is specified rather than copying and pasting the same exact verbiage over and over again, and then somebody trying to go through and parse it and understand, oh wait, are these the same or are these different? So we can do that with a window clause. So in this case, we have our sum of revenue over my window, because I'm very creative. And then we have our average revenue also over my window. And my window is defined at the very end of my statement. This way I can define it once and reference it repeatedly throughout my query. Any questions on that? Okay. So, in addition to being able to use window functions for a lot of standard aggregates that exist within Postgres, there are also a subset of specific analytical functions that are exclusively window functions. So some of these were also discussed in the talk yesterday, and I'm going to discuss a couple of them. So row number was discussed yesterday as well. It does exactly what it sounds like. It provides a single row number for every single row within your data set. You can partition it, or you could not partition it. You can order it, or you could not order it. Up to you. So in this case, I left my row number unpartitioned, even though I partitioned my actual aggregations. And we can see that now we have a row number 1, 2, 3, and 4 for every single one of my rows in my result set. Now, I'm going to go over rank because 1, it's kind of cool, but 2, because I've seen people make the mistake of trying to use rank the same way that they use row number. And that can be very, very dangerous. So if you think conceptually what a rank function does in math, if you have multiple values that are the same, they're going to be ranked the same, right? Whereas a row number is going to be distinct per row. So in this case, we have our rank ordered by country, or ordered by country descending, I should say, because I live in America, gosh darn it. And so when our results are displayed, our two suppliers that both are within the USA get the same exact ranking of 1. So this means that if you're hoping to use rank in the way that you might use a row number to identify individual records, you could very easily fail and not realize that you failed. So be very careful with how you're using this. The other thing I want to point out really briefly is the order by within your window clause is different than the order by for your general results display. So in this case, let's say I want to change the order of my output, my final output. So I've said I want to order it by supplier name. But my rank is still ordered by country. Okay, so in this case, the result set changes in how it's displayed, but the values are the same. Any questions on any of these? Okay.
How do you like order by the rank? Like,
How do you order by?
Do the previous one?
Well, what you could do is, so one of the things that you can do in Postgres is rather than specifying the individual, like the actual name of the columns, you can order by the ordinal number of the column. So in this case, I could have done order by 1, and it would have ordered by the rank. That's probably the easiest way to do it. Any other questions? Okay. So this is just a quick reference for you guys. The types of window functions that we have, in addition to all of the built-in aggregations, these are some of the analytical functions. You can look them up on the Postgres documentation. They're pretty cool. All right. Okay, give me a raise of hands again. Who's familiar with CTE'S? Who's familiar with recursive CTE'S? Okay. All right, so introductory. CTE is a common table expression. In Postgres, a lot of the time, it's known as just the with clause. One of the things to consider, and if you were in the talk yesterday, you already know this, but a CTE essentially allows you to take a subquery and cache it, almost like defining a temporary table within your specific query. So this is useful for a couple different reasons. One, if you need to reference the same subset of data multiple times, it's nice to be able to define it once, have it executed once, and then reference it throughout. The other thing is if you have a lot of nested queries, it becomes very difficult to read for a human being. And this allows you to break it up into smaller components and potentially build upon one another. The other thing to consider that I think people don't often mention is that common table expressions act as an optimization fence. So what that means is that the Postgres optimizer will execute it in a vacuum. It doesn't necessarily see how it's referenced in the rest of your query when it performs that the calculation. So this can be good if you know how to use it, or really bad if you don't realize this and hope that Postgres will optimize it in the context of your full query. So just something to keep in mind. So basic syntax for a non-recursive example. Let's say I want to produce a subquery that basically has my CTE for country, where I have my country and my count of customers. Then I have another CTE that does my country and my count of suppliers. And then I want to do a full join between them. And now I can see my list of countries with my customer count and supplier count for every single country. Any questions on that? Okay. Recursive examples. These are more fun and more difficult to understand. So we're going to start with a simple example of a recursive CTE. Let's say I want to get a list of numbers from 1 to 100. I'm going to start my with clause. I'm going to say with recursive keyword, give my CTE a name, and then some n value or variable. I then have values 1, which just gets you the number 1. I'm then doing a union where I'm selecting the n from my CTE plus 1 for as long as n is less than 100. Then I'm doing a select from that CTE, and I'm ordering by n. So this will produce a list of numbers from 1 to 100. I don't display them because it's long. Okay, how does this actually get evaluated? So I think this is for people who haven't used recursive CTEs, this is kind of the complex part of it. So we start out by evaluating our non-recursive term. So in the previous example, that was the values 1, right? So that gets evaluated. Then depending on whether I'm using a union or union all keyword, if we're using union, we discard any duplicates. And then we take the output of that and we put it into 2 places. We put it into the final result set of our CTE, and we also put it into a temporary working table. Then, for as long as our working table has some data in it, we continue to loop through these next 2 steps. So we start out by evaluating our recursive term, where we're taking the data that's in our temporary working table, and we're substituting it for the CTE in the self-reference. We're then performing the actual action, discarding duplicates again, assuming we have a union. And then with that new data, we put it into 2 or 3 places. 1, we put it into our final result set. 2, we put it into an intermediary table. We then replace the content of our working table with the content of our intermediary table and empty out our intermediary table. So it's essentially like having a bunch of buckets on your table and you're just moving data from one bucket to the other. And for as long as there is still data in the working table, this keeps going around and around and around. So let's look at a pseudo real-life example. Let's say we have a table of parts that has car parts in it. It has the whole, the part, and the count of elements. So in this case, we know that a car has 4 doors, an engine, 4 wheels, a steering wheel. Each door has a window. Each engine has a cylinder head. Each wheel has 5 screws, and each cylinder head has 14 screws. So let's say what I want to do is I want to find out how many screws are necessary to assemble the entire car. How do I do this? So we start out with our non-recursive term. We pull in the whole, the part, and the count from our original parts table, and I'm filtering to where the whole is the car. Okay? We then take that and we put it into our working table and we put it into our actual final result set. Then we're unioning our recursive term and our self-reference. So in this case, I'm selecting from my list, which is the name of my CTE, which in this case gets replaced with whatever is in the working table. I'm joining it to the original parts table, where the whole of the parts table is equivalent to the part of my list. And then the actual output that I'm selecting is the whole from my original CTE, because I want it to be the car. I'm pulling the part from the parts table, and I'm multiplying the count from the 2 tables together. Once this action gets performed, that data is dumped into our final result set, into the intermediary table, pushed into the working table, empty the intermediary table, and keep going again and again and again. So once all of this is done, we will see that the number of screws it takes is going to be 34. And, well, I suppose I should actually do a sum. So I don't know if you guys can see it in the back because it's at the very bottom, but I basically have this CTE, and then I do a select sum of the count from that CTE, where the part is equal to a screw. Okay? So, are there any questions on that? Yes?
So say you're traversing the street, there's a cycle in the street somewhere. Like, how do you tell it to only go like at 5 at most?
So it's based on whatever your definition is, right? So in my first example, I said to only go for as long as n is less than 100. In this case, because we keep joining back, at one point you're going to reach a point where there's nothing to join to. And so naturally when you try to join, you just won't have any records. So at that point your working table is going to be empty and the loop will stop.
Say it says that like a screw ship screws, there's that data in there.
If you have, so the question was, for anybody who didn't hear, if you have bad data that prevents your loop from stopping, what happens? At that point, you're probably SOL, to be perfectly honest with you. Because if you have a perpetual kind of self-reference, essentially, which is what you're talking about, it's not a self-reference from a table perspective, but from a true data perspective, then it's gonna execute forever.
One of the things you can do if you're worried about that is put a counter into your loop. So in your C query, you just start it at 1, and then in your iterative loop, just say I = 1, and just where I is less than 1,000. So it'll kill your loop eventually.
Yeah. It just depends on how well you know what you're doing, right? Because if you know that, oh, it shouldn't be more than 10, you can do that. But if you know that, oh, today it might genuinely be 5 loops, but tomorrow it might truly be 1,000, if you don't have an idea of what's an appropriate range for your result set, it's going to be harder for you to implement that kind of limitation. But you may have to pick something arbitrary that says, oh, even if it's valid beyond this point, it's not sufficiently performant. Any other questions? Okay.
Yeah.
Yeah.
So CTE can be replaced by temporary table, right? I think you mentioned.
Yep.
Okay. So from the functional perspective, right? How different is CTE from temporary table?
So 2 things. One, the non-recursive CTE can be replaced with a temporary table. The problem is that not all environments allow you to use temporary tables. Right? So for instance, I've worked in a couple companies now where we don't have access, either because they don't have logical replication for their followers, and so the replicas are read-only, in which case you don't have access to your temp space, right? Or if people are querying or performing some kind of functionality on the master directly, they also may not have write privileges of any sort, right? So not everybody is allowed to use temp space. The second component, though, is when you're talking about doing a recursive CTE, that's not really supported by a basic temp table. You'd still have to figure out some way to do your loop. So you could certainly do, a function of some sort if you wanted, but the CTE makes it easier where you can do it for your specific query without having to define it for the entire database.
But the query planner must be the same, right? I mean, the query planner shouldn't know the same difference.
Between what, like a
CTE.
function or?
Between the CTE and temporary table.
I'm not sure. Yeah.
Yeah, I can comment on that.
Perfect.
Actually, it should be better to use CTEs instead of temporary tables in a number of ways. For example, in a single backend, you create like several millions of temporary tables. I mean, you're creating, you're killing it. You will cause a really big load of system catalog because temporary tables done through like ordinary catalog. It's not visible from other backends, but you are loading it. And CTE is more or less harmless in that way. So there are some like installations with a system catalog going up to terabytes because of application are using temporary tables.
So it's definitely more flexible.
Yeah. Okay. So one thing to keep in mind is that CTEs can also be writable. So let's say, using our previous example, I said, oh, really, I want to remove and archive all of the records that had the car as the whole. Let's say I want to archive them into a separate table. So what I can do is I can write my CTE in the same way that I would before, but within my CTE definition, I actually have a delete statement. So in this case, I'm deleting from parts where the whole is equal to a car, and then I'm returning from my CTE the actual values that are being deleted, and then I'm inserting them into a separate archive table. So it has some convenient use cases. Same thing with recursive CTEs. They can be writable as well. So let's say in this case, I have the exact recursive CTE that I had before, but now rather than making people continuously reference our original parts table, let's say I want to materialize my pre-aggregated table that goes through and says, hey, let's start with the car and show all of the parts that are necessary for that car and their counts. And I want my users to be able to use that. So in this case, I'm inserting the output of that CTE into my car parts list table. And when I select from it, I get something like this. Let me backtrack a little bit because I think I skipped this. A couple caveats with CTEs. So again, I'm not going to go through all of these, but I want you guys just to be aware that you do need to be careful with how you use them. For one, it's not actually recursion, it's iteration, which probably doesn't really matter for you. You also have to be careful again with how you're using union versus union all, what kind of references you have, so you can't have two CTEs that are both referencing each other, things of that nature. So if you're going to be using a lot of CTEs, just take a look at the documentation and see what kind of limitations you're going to run into. Okay, I'm going to go through this pretty quickly, but lateral is a pretty new-ish join type within Postgres. It got added in 9.4. Basically, what it allows you to do is it allows you to have a subquery within your join criteria that references your outer query. So when it comes to set returning functions, it's automatically implicit, whereas for regular queries, it's not. So in this example, let's say I want to generate a series of numbers from 1 to 10, and then I want to use that table that has my list of 1 through 10 to generate another series from 1 to the maximum number of that row. So in this case, I could write it in two ways. I could specify the lateral keyword, or I could not. The result is going to be the same. So if we start out with our original max number, we see for 1, we generate a series of just 1. For 2, we get 1 and 2. For 3, we get 1, 2, 3. And it keeps going for all 10 numbers. Now, how is this relevant to most use cases? So let's say I had a query like this, where I wanted to have 2 subqueries within my join criteria. I'm starting out with all of my customers whose first name starts with S, because I'm narcissistic. And then I want to join it to all suppliers who function within the same country as my customers. So when I try to perform this kind of correlation within my join, Postgres tells me this. It says, hey, I know that your table exists, but I can't do this. So how do I actually accomplish this? By adding this one little keyword, lateral, now my query works perfectly fine. So it literally allows you to have that correlated subquery functionality within your join criteria. Now, you could also rewrite this with something like this. That's not always the case, but in my example, you could rewrite it like this, where you have a correlated subquery within the join criteria itself. But this is really messy, and nobody wants to do that. And it's not as optimized. Questions? Perfect, and I think my time is up in like 30 seconds. So if you guys have questions for me, feel free to catch me during lunch or in the hallway. I'll be glad to explain stuff. Also, once the slides are posted, I actually have a reference to the Postgres documentation for all of these subsections, so you can reference it if you need to. And these slides are actually already posted on the Postgres wiki under the slides for the PGConf EU that was in Estonia last week.